A secondary example of being able to evaluate a double integral utilizing a set of polar coordinates. So we have double integral 1 over 1 plus x squared plus y squared to the 3/2 dA, where A, or D, excuse me, is the region that's going to be bound in the first quadrant once again, enclosed by the circle x squared plus y squared equals 16. All right, so here's what we have. Clearly, x squared plus y squared equals 16. R squared is 16, or r is equal to 4. Limits of integration for theta. On the x-axis, theta is equal to 0. And then up here, right on the y-axis, theta is equal to pi halves, just like the previous problem. So when we set this up, we are going to have r is going to range from 0 to 4. All right, and again, if you can imagine one of those polar rectangles, get something like this. Okay, so we start with the radius being 0, and the radius goes up to 4. The change in theta is going to go from 0 to pi halves. Right, so that should be fairly easy to set up. We're going to use a substitution. So our substitution is going to be integral 0 to pi halves, 0 to 4. We're going to have 1 over the quantity of 1 plus, instead of x squared plus y squared, 1 plus r squared to the 3/2 power. And then instead of dA, we're going to have r dr d theta. All right. So hopefully that's not too difficult for you to be able to translate. Next thing we're going to do is we're going to prepare this for integration. Right? We can split it up into two separate integrals because all of the bounds are constants. So 0 and 4 is a constant, 0 and pi halves is a constant. So let's rewrite it as such. I get integral 0 to pi halves of just d theta, which isn't too bad. Then I also have, I want to multiply that by the integral from 0 to 4, r 1 plus r squared, forgot the square in that, so 1 plus r squared to the negative 3/2 power dr. All right, a trick that might save you some time. If the limits of integration, or if you have an integral of just d of whatever the variable is, so d theta, dr, dx, and both of the bounds are constants, all you have to do is just take the top bound. All right, so this is just going to turn into pi halves. If you don't believe me, just say theta goes from 0 to pi halves when you do the antiderivative, and then once you get that, that's just going to clearly turn into pi halves minus 0, which is just going to be pi halves. This other animal, not too difficult. Again, we're going to utilize a u substitution. You could use a trig substitution if you wanted to, where r is going to be equal to tangent of theta. Let's just use a u substitution. Let's say 1 plus r squared is going to be u. du is going to be 2r dr, and that's very helpful because we need an r dr. However, we don't need the 2, so half of du is going to be r dr. We're in good shape. We're going to do the substitution. We can't forget about that pi halves, so I'm going to carry down the pi halves each time. Now we're going to have integral. We change our limits of integration from 0 to 4 to a to b. Remember we said that u is going to be 1 plus r squared, so now we get u to the minus 3/2. But then we also have a du over 2. Right? Not a difficult integral to evaluate. I'm going to move the 2 on the outside, or the 1/2. So now we get pi fourths. I'm going to add 1 to negative 3/2, so I get minus 1/2 to the u, divided by minus 1/2. And that's going to range from a to b. we're going to go ahead, we're going to flip the order, or we're going to flip the denominator. So now this just becomes the opposite of pi halves by dividing by the negative 1/2. I'm going to back substitute for r, so that's 1 plus r squared to the minus 1/2 power. And then r, if you recall in the original problem, was from 0 to 4. Okay, so we go back up. Don't forget what r was. R went from 0 to 4. So we go back down here, 0 to 4. This is not a polynomial, so we do have to concern ourselves with substituting 0 and substituting 4. So we're going to substitute 4 back in, so this is minus pi halves, 1 plus 4 square to the minus 1/2, minus a negative pi halves, 1 plus 0 square to the minus 1/2. Evaluation. This just becomes root 17. So this is going to be minus pi over 2 roots of 17. Right? If you don't believe me, go back, check the algebra. This just turns into pi halves times 1 to the minus 1/2. So pi halves of 1 to the minus 1/2. All right, otherwise known as just 1. So another way to rewrite this is you could rewrite it as pi halves minus pi over 2 root 17. If you wanted to get a common denominator, you would multiply both by root 17 over root 17. So we could write this as pi roots of 17 minus pi over 2 roots of 17. If you want to rationalize it, that's fine. If you want to leave it as is, that's fine. This is probably a pretty precise answer. We could even factor out a pi halves from that, but I think that would be a sufficient answer. So go back, try to work through that again on your own. Just make sure you're all right with setting it up and evaluating with the techniques of integration.